Hey folks, I've got a few more Newton's second law examples. We'll see how many we get through in this one. The first one is a classic statics example, and it is what I would call the stoplight example. So let's say you have a pole and you have a stoplight, and let's say it's being held by two different strings like so, or ropes or cables, and they're at different angles. And I'm going to give you the angle with the vertical on this one, we'll say is 30 degrees. And then the angle with the horizontal on that one, let's say is 40 degrees. Okay. And we'll call this left hand one T1, tension 1, and we'll call this right hand one T2. Okay. And let's say the stoplight weighs 300 pounds. And for this problem, we're going to go ahead and use numbers. Most of my problems I won't, but in this one I will, just to give you a flavor for what the numbers are. And also I'm going to use pounds instead of kilograms or newtons, just because that's what we're familiar with. So the real simple question is, what's the tension in each rope in pounds? Okay. So your first step here is to realize that the stoplight is not moving, and therefore it's not accelerating, and therefore the net force in any direction I choose has to be zero. Okay. So we're going to draw our two FBDs like we've been doing. So the first FBD is what forces act. So here you have the force of gravity, which is given in pounds as 300 pounds. Okay. And then you have T1 kind of going like this, and you have T2 going like that. Okay. Now, one of the things we're going to answer in this problem is which one's bigger, tension 1 or tension 2? First time through, students might say tension 2 because it's a longer cable. It turns out that that's exactly wrong, but turns out T1 will be bigger. It's carrying more of the load, more of the weight. All right, so there's our three forces acting on the stoplight. Now we're going to break these down into components. And for the sake of ease here, it doesn't matter which two directions you pick. You can pick any two directions you want here. But I'm going to pick just the vertical and the horizontal, okay? And therefore, gravity is vertical. I won't have to break gravity down to components, okay? So, and again, a reminder, this angle here is 30 degrees, and this angle here with the horizontal, it's going to be congruent to that one, is 40 degrees, okay? So if I break this stuff down into components, I'll do that down here. You got FG still pointing straight down. So FG is 300, okay? For T1, you've got a component pointing up, which would be, that's the adjacent leg to our 30-degree little triangle, little right triangle here. Imagine a little right triangle there. So our adjacent leg is cosine. So this would be T1 cosine of 30. And that rope also, or that cable also is directed left. So that would be T1 sine of 30. Okay. For T2, now there we're given the angle at the horizontal, so it's going to be slightly different. The vertical component, that's the opposite leg in this little triangle, so that's sine. So this upward component would be T2 sine of 40, and the horizontal component would be T2 cosine of 40. Okay. Now, by the way, if you've done that and if you've got that down correct, the rest of this is actually just a little bit of math. These two parts here are the critical parts. Drawing the FBD with the forces as they lie, and then being able to break your forces down into components that are parallel and perpendicular. Now, notice in this one, there's no motion, so I'm not saying parallel to the motion or perpendicular to the motion. I'm just saying parallel and perpendicular to gravity. All right, so I'm keeping gravity. I'm not breaking that one down, the components. All right, now if we look in the horizontal direction, so I'll say the x direction, okay, we know the net force in any direction has to be zero here because the stoplight's stationary. It's static. It's not moving. It's not accelerating. So in the x direction, if we assume right is positive, I would have a negative T1 cosine of 30, okay. Oh, sorry, and I messed that up. Let me try it again. You would have a negative T1 sine of 30 plus T2 is cosine's 40 to the right, so you'd have T2 cosine 40, and that's your only two horizontal forces, and they have to add up to 0. Okay, so I'll call that equation 1. Equation 2, we're going to look in the y direction, in the vertical direction. I'll say up is positive. So there you have a T1 cosine 30 acting up. You have a T2 sine of 40 acting up, and then you have minus 300 acting down, and that equals 0. Okay, so now you've just got two algebra equations, two unknowns. You're just solving and doing algebra. For equation 1, I will get T2 by itself. So if I move the T1 sine over to here and then divide by cosine 40, I get T2 equals T1 sine of 30 over cosine of 40. And then I'm going to take this and sub it in there, and then I'll have an equation with only T1s in it. So we've got T1 cosine 30 plus this crazy fraction, T1 sine 30 over cosine 40 times sine of 40. And I'll move the 300 over to the other side, so equals 300. And so now we're just doing algebra. If you plug cosine 30 into your calculator and then plug all this into your calculator and add them up, when I did that, I got 1.2856 T1 equals our 300, and I end up with T1 equals 233 pounds, okay? And then you go back and plug this in here to determine T2. And when I plug those numbers into my calculator, I got 152 pounds, okay? So notice that T1 is significantly larger than T2. T1 is a shorter cable that has a steeper angle, okay? Another thing to note is a common error the first time students may do this is they may say something to the effect of, oh, well, T1 plus T2 has to equal 300. No, they don't. They have to more than 300 because there's not only are there vertical components for each of these, there's also horizontal components for each of these that have to cancel out. So the two vertical components of T1 and T2 do indeed add up to 300, but T1 and T2 overall add up to more than 300 because they have a horizontal component. Okay. Now I'll go ahead and do a second example, which is way different than the first one. So let's say you've got the following situation. Here you got the ground, and you got two boxes. We'll call this M, and we'll call this 4M. Okay, that's the relative masses, and they're on wheels, so there's going to be no friction here. We're going to ignore friction, and I'm going to apply a force F to this two-cart system. And what I want to know is what's the acceleration of the system, and also what's the force between the two carts. In other words, the single M is pushing the 4M how hard? In terms of the givens and fundamental constants, meaning there's no numbers here. I mean, there's a 4 there, but I'm going to leave everything in terms of F and M and fundamental constants, okay? So we start by drawing an FBD. Now, there's a couple ways you could approach this. One way is to look at how many objects there are and draw an FBD for each object. So here we have the single M, okay? You have a force F acting on it, and you have the 4M pushing to the left. And that's, I'll call that the force of contact, but that's really a normal force, okay? But that's what we're trying to find. We're trying to find what is that force of contact, okay? You also would have mg acting down, and I'll call this the normal force Fn1, the ground pushing up on it, which in this case would equal mg, okay? And then you're going to have the 4m cart, okay? Now, what's pushing the 4m to the right? Is it F? No, this force ain't touching that 4m cart, so you can't say F is acting on it. What is touching the 4m cart is the 1m cart, your force of contact. Okay, so by the way, this force here and this force here are equal. That's Newton's third law. M pushes 4m to the right, 4m pushes little 1m to the left. They're equal and opposite forces. There is no leftward force on the 4m. There's nothing resisting it. You would have a 4mg acting down, and then I will call this Fn2, Okay. Now, by the way, I labeled this and this differently because they are different magnitudes. So you should label them differently. Anytime two forces are not the same, they should not be labeled the same in your FBD. So if you have multiple forces of gravity or multiple normal forces, you need to distinguish them somehow. All right. Now, what's going to be the same for both carts? Well, they're attached. They're both going to have the same acceleration. Okay, so that's an easy one. They're both going to have the same acceleration. So let's look at the 1m first, and I'm just going to focus on the horizontal motion. So net force parallel to the motion equals ma parallel to the motion. For the 1m, I have an F to the right, and I have the Fc to the left, and that equals ma. So I've got an equation with several variables in it. For the 4m, if I do the same thing, I only have Fc, and that equals 4m times a, okay, because that mass is 4m. Okay, so there's my second equation. Okay, now what I can do next is if I write these two equations down one above the other, I want you to notice something, and we'll do this several times this semester. So here's the first equation I wrote, and here's the second equation I wrote. Okay, what we're going to do is we're going to just add the two equations together. So on the left side of the equal sign, F minus Fc plus Fc is simply F. And then here we have an Ma plus a 4Ma, that's 5Ma, and A equals F over 5M. Okay, so there's your acceleration. And then to find your force of contact, you plug that back into either equation. I'll pick this one because it's just a little simpler. And you get Fc equals 4M times F over 5M. Now notice that the m's cancel, and you get Fc equals 4/5 of the pushing force. Okay, and that makes sense. This mass is 1/5 of the overall mass, and this mass is 4/5 of the overall mass. So the 1m over here, if we know Fc is 4/5 of F, F minus 4/5 of F is 1/5 of F. So it takes 1/5 of the overall force to push the 1/5 of the mass. And then here, Fc for on the 4m cart is 4/5 F. So that takes 4/5 of the overall net force to push the 4m cart. So that kind of makes sense. All right, so I'm going to have another video after this with another example that has multiple objects moving. Hope you found this helpful, and thank you very much.